Back in 2022, a truly remarkable picture was released. What makes it so special? This image stands as one of the most detailed radio views ever captured of our galaxy's heart. Created from the first complete survey using the full power of the Milky Radio Observatory in South Africa, this picture required 3 full years of data analysis to finish. And it is showing us something completely strange. Hidden within the violent turmoil at the Milky Way's core are hundreds of highly organized, thread-like structures, hanging mysteriously above and below the galactic center. These puzzling filaments stretch for distances up to 150 light-years, yet they are only between 1 and 3 light-years wide. The major question is, what exactly are these enormous cosmic threads? Now, researchers are working to decipher this meerkat image to find the answer. Today, we will delve into the mysteries surrounding one of the Milky Way's most bizarre phenomena. We will look at the fortunate accident that led to their finding and the extreme traits that continue to puzzle scientists. The center of our galaxy, located some 27,000 light-years from Earth, is a violent place. This innermost area, known as the Central Molecular Zone, covers about 1,600 light-years and is by every measure the most extreme region in the entire galaxy. The density, temperature, and turbulent motion here are roughly 10 to 100 times greater than anywhere else. The cosmic ray energy density, which indicates energetic activity, is hundreds to thousands of times higher. This zone contains enormous complexes of molecular gas, amounting to about 20 million times the mass of our Sun, along with thick cosmic dust clouds, ionized plasma, intense cosmic ray energy, ultraviolet and X-ray radiation, and chaotic magnetic fields. It is a hotbed of cosmic action, from star birth to supernova explosions. And of course, there is Sagittarius A, the supermassive black hole at the very center, with a mass 4 million times that of our Sun. These conditions are incredibly exciting for astronomers, but they also make the galactic center famously difficult to image. Visible light cannot pass through the dense clouds of dust and gas. So scientists use other parts of the electromagnetic spectrum to pull back the curtain and see the secrets at the galaxy's core. Radio waves have the longest wavelengths in that spectrum, ranging from a few millimeters to hundreds of kilometers. Wavelengths from millimeters to tens of meters are perfect for radio astronomy. They pass right through the obscuring clouds, giving us an unobstructed view of what lies below. In the early 1980s, Farhad Yousafzadeh, who was working on his PhD, used the Very Large Array Telescope in New Mexico to make a radio map of a section of the galactic center. He intended to study star-forming regions, but narrow streaks of radio emission were slashing across his entire survey area, right through the parts he wanted to examine. He thought they had to be artifacts or errors in the data, which any researcher will tell you is incredibly frustrating. After much annoyance and no success in fixing these supposed errors, he went back to the VLA to image the same area at a different radio frequency. That was when he had his breakthrough moment. Early one morning at 4 a.m., he was comparing the 2 sets of data, taken at different times and wavelengths, and he saw the same structures in both images. This was no mistake. This was a real discovery, something unlike anything he or anyone else had ever encountered before. Zadeh was seeing highly ordered structures in a place where only chaos was believed to exist, and they had some very odd features. Most striking was their immense size. These were continuous, narrow ribbons of radio emission, between 50 and 100 light-years long, but only 1 to 3 light-years wide, hanging vertically above and below the extreme central molecular zone. Some appeared in pairs or groups running parallel to each other like harp strings, each spaced apart by a consistent distance of about 1 astronomical unit, which is the distance from Earth to the Sun. When he compared them with infrared data from the same area, Zadeh also found they had no matching signal in that part of the spectrum. This told him they were non-thermal emissions, meaning they were not produced by hot gases. This was supported by other measurements, like spectral index and polarization, which showed the filaments were highly magnetic and emitting something called synchrotron radiation. Synchrotron radiation happens when electrons moving near light speed interact with a powerful magnetic field. This raised a big question: what could possibly accelerate electrons to such incredible speeds? The emissions were continuous along the full length of the structures, ruling out localized events like star formation or supernova remnants. So Zayday named them non-thermal filaments and suggested they were probably linked to galaxy-scale phenomena. For a scientist, a discovery like this would be an absolute dream. After all, what better gift than unknown galactic structures that no one has ever seen? His observations did not match anything else known in the galaxy, and Zayday was left with many questions. Where did these non-thermal filaments come from? What maintained their linear shape over such vast distances of space and time? And why, when they clustered together, were they so evenly spaced? But almost as soon as this amazing discovery was made, the trail began to grow cold. The telescopes available at the time simply were not sensitive enough to provide answers. Over the next 35 years, only a few other vertical non-thermal filaments were found and studied. Some were even given mysterious names like the snake, the pelican, and the bent harp. Sadly, there was not enough data to make any major progress in understanding them. That is, not until 2022 and Meerkat's astounding image. The Meerkat radio telescope at the South African Radio Astronomy Observatory consists of 64 linked antennas, each with a 13.5-meter parabolic dish, spread across 8 kilometers of radio-quiet land. Built over 4 years, the full array was officially opened in 2018. Its location in the southern hemisphere is ideal for imaging the Milky Way's center, thanks to the sun's axial tilt relative to the galaxy's plane. Using L-band radio frequencies, equivalent to wavelengths between 18 and 35 centimeters, they split this area into a 20-part mosaic, surveying each tile over a total of 144 hours. This was the first use of Meerkat's full array, with 60 to 62 dishes collecting data at any one time. After generating 70 terabytes of raw data, comparable to 700 hours of 4K YouTube video, the team then had to process it all. That was a huge task. This is a common technique for smoothing edges, removing background noise, and enhancing fine details, which was especially important for seeing the non-thermal filaments clearly. And this is what they got. Looking more like a work of art than a scientific dataset, it reveals a wealth of features. Some are well known, like Sagittarius A, seen in the central bright area, and clearer views of previously known supernova remnants and star-forming regions. Here is a supernova remnant. As the team noted, one of the most startling discoveries was the sheer number of filaments visible in the image. There were 10 times more than all previously known, most of which had never been seen before. This was a game changer for Zayday and his colleagues. He said they could finally see the big picture, a panoramic view filled with an abundance of filaments, calling it a watershed moment for understanding these structures. There was finally enough data to do meaningful population studies. They got to work performing statistical analysis on the filaments. This work, published in the astrophysical journal Letters, not only describes the filaments further, but offers intriguing clues about their origin. The new data confirmed that all of them are magnetized. In fact, the team found the magnetic field was much stronger, in some cases 10 to 100 times stronger than typical galactic magnetic fields. The new analysis also confirmed that synchrotron radiation is a defining feature. Interestingly, the Meerkat data showed a steepening with galactic latitude, meaning the filaments appear to cool as they stretch away from the galactic plane. This gives us a clue about their possible origin. The electrons farther from the plane could be older, suggesting the filaments are related to past activity from Sagittarius A. There was another clue pointing to this: enormous structures known as radio bubbles. First discovered by Haywood, Zayday, and the Meerkat team in 2019, these huge radio-emitting structures stretch symmetrically above and below the galactic plane, forming an hourglass shape thousands of light-years across. They are thought to have been created by a phenomenal outburst from Sagittarius A between 100,000 and 1 million years ago. An event powerful enough to leave such a mark on the galaxy, could have been caused by vast amounts of gas and dust falling into the black hole, or a huge, sudden burst of star formation nearby. An incident like this would have triggered an intense energy outburst and whipped up galactic winds, violently driving gas and cosmic rays away from the center, stretching and amplifying magnetic field lines in its wake, creating those bubbles and the non-thermal filaments. Furthermore, strong magnetic fields, which we now know are a confirmed trait of all filaments, can trap cosmic rays, and we can actually date them. The cosmic rays detected in the filaments by Milky match the proposed time period of the Sagittarius A outburst thought responsible for the radio bubbles. In other words, they are the same age. Milky's position and capabilities, along with the same high-pass filtering used to resolve the filaments, not only revealed these bubbles in amazing detail, but showed that nearly all the filaments are contained within them. This close physical connection adds even more weight to the idea that the same energetic event created both. Something powerful enough to make the bubbles would definitely be able to accelerate electrons to near light speed, with the stretched magnetic field lines channeling them to produce the filament's signature synchrotron emission. With this hypothesis in mind, Zayday and the team described the formation of non-thermal filaments as magnetized streamers in a cosmic ray-driven wind. It certainly paints a compelling picture for their possible origin, but it is not yet conclusive, as the authors themselves state. Other theories are being developed. With a mystery this enticing, other astronomers have been studying the filaments too, but this single image remains the one that has told us the most. Zayday was not exaggerating when he called it a watershed moment, but with so many unanswered questions, some going back 40 years, where does that leave us? Are non-thermal radio filaments just a galactic oddity? Not at all. They are a riddle wrapped in a mystery inside an enigma, and could shed light on one of the biggest unanswered questions out there: how supermassive black holes regulate star formation within a galaxy. Scientists know that the active centers of galaxies must transfer energy and matter into interstellar space through a process called galactic feedback. If they did not, star formation would run wild, using up a galaxy's gas and dust far faster than what we actually observe. But how this feedback happens is unknown. Milky's detailed imagery of the non-thermal filaments and the radio bubbles gives us strong evidence that this outflow of energy could happen in discrete but extremely powerful outbursts. This is something that has been seen before. Fermi bubbles, discovered by NASA's Fermi Gamma Ray Telescope in 2010, are even larger hourglass-shaped structures spanning a total of 50,000 light-years. These unimaginably massive formations are thought to be millions of years old, likely caused by a violent outburst from Sagittarius A that calculations suggest had the energy of 100,000 supernovae. This event was much more powerful and ancient than the one proposed to have made the filaments and radio bubbles, but together they paint a picture of intermittent outbursts from deep within our galaxy's heart. Both have the potential to regulate star formation, ensuring the Milky Way does not burn out too quickly. As researchers continue to unravel the mysteries of non-thermal filaments and tackle the big questions about how the universe works, the trail does not seem to be going cold again anytime soon. Since that first full-array image, Milky has found more of these mysterious strands in other galaxies, with very similar properties to the ones we see in the Milky Way. Their existence elsewhere suggests a common underlying mechanism and hints at their role in fundamental galactic processes. To conclusively piece together the whole picture will require another leap in imaging resolution. Hopefully that is not too far off. Milky, already honored by the Royal Astronomical Society for its spectacular radio astronomy observations, was built with longer-term goals in mind, specifically to be part of the Square Kilometre Array. With a total collecting area of 1 square kilometer, it will be 50 times more sensitive than any other radio instrument and is expected to be fully built by 2028. Watching developments in other parts of the electromagnetic spectrum will be important too. Zayday believes the next big breakthrough will come from gamma-ray telescopes. Imaging at higher frequencies yields higher resolution, which could potentially show us whether the filaments, the radio bubbles that contain them, and the vast Fermi bubbles are all connected. There is an elegance in order rising out of chaos. Observing non-thermal filaments streaming out through cosmic winds certainly fits that idea, so keep your eyes on the cosmos. With images and phenomena this spectacular, it is an absolute pleasure to do so. If you found this journey into the galaxy's heart as fascinating as we did, help us keep exploring by subscribing and hitting the like button. Sharing this video with a fellow space enthusiast helps spread the wonder. Thank you for watching Pectacular. It is an absolute pleasure to do so. If you found this journey into the galaxy's heart as fascinating as we did, help us keep exploring by subscribing and hitting the like button. Sharing this video with a fellow space enthusiast helps spread the wonder. Thank you for watching.